Hey everyone, just wanted to welcome you to Week 2, Module 2 for ME 111 System Dynamics. This chapter we're going to be covering dynamic response methods. A couple things that we should be able to accomplish by the end of this module. Number one, we should be able to apply the separation of variables or the Laplace transform method, whichever is appropriate, and determine when each of these is appropriate in order to obtain a solution of a linear differential equation model. Second, we're going to be able to identify free, forced, transient, and steady state components of the complete response. Number three, we should be able to identify and interpret the time constant, oscillation frequency, and damping ratio. We'll go over the key equations for these, as well as some applications in our lecture slides. Four, when we're applying the Laplace transform method, we should be able to perform the appropriate expansion and apply the appropriate transform properties to obtain the inverse transform. Whether we're doing these by hand or using MATLAB to do these, we need to understand this method. Number five, we should be able to obtain transfer functions from models expressed as single equations or as sets of equations. And we should be able to evaluate the effects of pulse and impulse inputs and input derivatives on the response. Lastly, we're going to go over some MATLAB as it applies to all of these different methods throughout the chapter, so we can take a look at how we solve them by hands, how we can plug it in and get the code from MATLAB as well. So before you jump into the lecture slides or start doing the quizzes and the homework, what I'd like you to do is to take the time to go through the textbook and do the required readings. So the text will be covering Chapter 2. The first lecture will cover sections 1 through 4. Our second lecture will cover sections 5 through 7. And our third lecture will cover sections 8 through 10. So you should read each of these sections of the textbook before jumping in to any of the lecture slides or starting any of the quizzes. Speaking of quizzes, we have some assignments this week. First thing is we have our first homework assignment. So take note that this homework assignment will be due the 14th by 4 p.m. If you have any questions on formatting, how to submit it, how it will be graded, please contact me. And also reference Blackboard. I have some of the homework guidelines listed up there as well. You're going to be submitting this through Blackboard as a PDF, upload it, and it'll be graded based upon the rubric on Blackboard. Next thing to do is our second reading quiz. Similar to the first reading quiz that you took last week, multiple choice. This will be due on the 11th by 4 p.m. as well. So Module 2 will be broken down into 3 lectures, 2.1, 2.2, and 2.3. So take a look at Module 2.1 for the lecture associated with that. In this section, we're going to be covering differential equations and the Laplace transform. So we're going to introduce some important concepts and terminology associated with differential equations, some of the basic stuff that we're going to start with and expand upon it, and the present methods for quickly solving simple differential equations. So what methods do we have available to us? What resources can we use when we're solving these differential equations? We're also going to introduce the concept of free, forced, transient, and steady state response. We'll be covering a couple different applications as we go through this section as well, hydraulic applications, and you'll have some problems related to that. As far as what's related to the textbook, this will be sections again 2.1 through 2.4. 2.1 being differential equations and how to solve those, going over some of the basics, response parameters and stability, Laplace transform method, and solving equations with the Laplace transform method. Again, we're talking about solving these simple ODEs. One of the ODEs right here, definition is an equation containing an ordinary but not partial derivatives or a dependent variable. We'll go through some other basic definitions of some of the standard differential equations we're doing and some of the standard definitions of the solutions that we're going to be using with these when we're solving these simple differential equations. Our next lecture is going to be lecture 2.2, transfer functions, pulse, and impulse inputs. So we'll talk about all of those. Section 2.5 in the book covers our transfer functions. 2.6 covers our pulse and impulse inputs. And 2.7 we talk about partial fraction expansion. So one of the key equations we'll be using I've listed here. We have the concept of the transfer function is useful for analyzing the effects of this input. We want to consider this model here in this general form of x dot plus ax is equal to the function f of t. Our last lecture for Module 2 is going to be Lecture 2-3. This is where we're going to go over some of the MATLAB. Now, if you've already gone through the actual lectures for 2.1 and 2.2, you'll notice that I've gone through and utilized MATLAB in a lot of the sample problems and example problems that I've gone through as my hand solutions. That way you've kind of already been introduced to this, but in this last one, I'll go over some more of the specifics of what toolboxes to use, some of the functions you can utilize, And speaking of that, one of the things you really want to do if you haven't done it yet is within your copy of MATLAB, whether you have your own personal copy or downloaded the one through the university, make sure that you have your symbolic math toolbox add-in functioning and ready to go. And also, you may want to consider coming down and making sure that you have your MATLAB control system toolbox readily available as well. Within the symbolic math toolbox, that's where we're going to get these Laplace and inverse Laplace functions that we can use for those transforms. And with our control systems toolbox, we can then do some of these linear, time invariant, and constant coefficient differential equations. So some of these ODE solvers are very powerful tools that we can utilize. So make sure you have both of these toolboxes ready to go within your copy of MATLAB.